Hi, I'm Dr. Prathana Ghosh, and today I'm going to talk about shear force bending moment diagram by using internal shear and moment equation. So, what is our lesson objective today? Develop the internal shear and moment equation for various segments of the beam. Then we are going to compute the values for shear and moment at various locations, most of the important locations, and then we'll draw the shear and moment diagrams for the whole beam. So, to do so, we need to go to an example problem. So here is the example problem. So what we are having? We are having an overhanging beam, internal beam, external roller, and the other portion is overhanging, AB portion. A is the free end. So we have altogether 21 plus 9, 30 feet of span of the beam. We have to draw shear and bending moment diagram for this overhanging beam using internal shear and moment equation. So let's go step by step. So first step, what we need to do? We need to draw the free body diagram and find all reaction, all vertical reaction and moments at the supports from static equilibrium equation, as you know. Then we need to think about how many segments are required to solve the problem. As you see here, we have two segments, AB and BC. So we will cut within each segment at a generic distance x. So we can start from A or we can start from C. Either way you can start. Generally, we start from left side. So at a generic distance x, we'll cut it and we'll generate our internal shear and moment equation. So in the first segment, x will range from 0 to 9 feet. Then when it goes to the next segment, BC, x will still start from A. We are cutting within BC. So x will range from 9 to 30 feet. Now just keep in mind that here we are going to generate in each segment one shear and one moment equation. So we have now two segments. So we have two shear and two moment equation. And one of the important thing also we need to remember, how do we know how many segments we will need for a particular problem? So wherever the support changes and load changes, then the new segment starts from there. So as you see, we have support at B where you have upward reaction. Obviously, your loading condition is going to change from there. That's why we have two segments. So once you generate the shear and moment equation each segment, then the next step will be find out the zero shear point if we have any within the beam. So that's very, very important. Why? Whenever we have zero shear point, that will be the highest bending moment development in the beam. So sometimes you could have zero shear point, sometimes you couldn't. We just need to verify it. Sometimes you could have also zero moment point. That point is called as inflection. So once you develop all of these important points, then we are going to put the values of x at those important locations, starting from A, any zero shear point, then at B, then at C. And then once you put all those values, then you have to think about how the nature of the equation. If the equations are straight line, then obviously your diagram will be linear. If the equation is quadratic or cubic, then the diagram will be curved. So what kind of curve? If you have curved diagram, it could be concave up or concave down. How do you know? So if you have positive bending moment, obviously concave up. If you have negative bending moment, concave downward. So being said that, now we are going to solve this problem by using internal shear and moment equation. And then we have a one practice quiz problem, which I'll show a little bit later on. So I'm going to unshare this and then I'm going to work on this example problem in Microsoft OneNote. So let's solve the problem in Microsoft OneNote. So we are having, we are having our overhanging beam A, B, and C. A to B is 9 feet and B to C is 21 feet. And all the way A to C we are having distributed load, rectangular uniformly distributed load, which is 7 kip per feet. So our first step, find the reaction. So we have our By we have our cy particle reaction. So let's do that. Taking the moment about c. So if we take the moment about c, one of the support, 7 times 30, and it is exactly acting in the middle. So let's call this here 7 times 30. And distance is exactly in the middle, so 15 feet. Just to show it. That is going to create counterclockwise moment, and then by times 21 clockwise. So your by becomes 150 kips. Once you get your by, then we'll get our other reactions. Your summation of Fy is 0. By plus Cy minus 210 is equal to 0. From there we are getting our Cy is 60 kips. So By 150 kip upward, Cy 60 kip upward. Then we are going to do our internal shear and moment equation. So first segment we are going to do 0 to 9 feet x within AB. So our aim will be starting from A, we are cutting within AB. B has not yet reached. So the distance x we are cutting. Our aim to find out V and M. So 7 times x, it is still 7 kip per feet. Height didn't change. And distance is x over 2. The summation of Fy is 0. So that gives your negative 7x and V. Both are downward negative. So V is negative 7x. Equation 1. Then moment equation. So step by step, aim counterclockwise positive. 7 times x and distance is x over 2 counterclockwise moment is creating. So aim is negative 7x square. Equation 2. So first shear and moment equation in first segment we have developed. Now our aim to go for second segment. So we are still cutting within this C. So x will be ranging from here. We are cutting a distance, somewhere generic distance. So what will be the best way of deciding the shear and moment equation? It will be from the other side. So if it is x from this side, how much will be the distance? Total is 30. So this will be basically your distance within 9 to 30 feet. So 30 minus x, as you can imagine. So let's do that. So we are now cutting from other side. C is there. Cy, we have 60 kip. We are cutting from the other side. So distance will be now 30 minus x. And still rectangular distributed load. So V will be up from this side. As we know the sign convention, aim will be clockwise. And your height of the loading is still 7 kip per feet. Base is 30 minus x, so your equivalent concentrated load will be 7 times 30 minus x. What is this distance? 30 minus x over 2. So let's do that. Again, summation of Fy is 0. Cy is there, upward. 7 times 30 minus x is downward. And v is downward. So if you do the math, v becomes cy minus 30. 7 times 30 minus x is 60 minus 7 times 30 minus x. Equation 3. The name negative m clockwise, as you see. Cy times 30 minus x counterclockwise. And 7 times 30 minus x, and distance is 30 minus x over 2 clockwise moment. So we are just simplifying a little bit, not fully, so that we can plug in the value of equation 4. So now I need to think about where is the zero shear point. So if you see here, in the first segment, when x equal to 0, v is 0. There is no in between points where zero shear can happen, but it could happen in the next segment. So if we put v equal to 0, 60 minus 7 times 30 minus x is going to be 0. So let's plug in the equation. 60 minus 210 plus 7x is going to be 0. So 7x minus 150. So that gives x equal to 21.43 feet. Very important point. BM will be maximum at that point. So let's plug in the values. All of the values, each of the values that we have determined. So x equal to 0 feet, v 0, just seeing the equation 1, m 0 k feet. We know that it is free end, x equal to 9 feet, v equal to minus 63 k, equation still 1, m negative 283.5. Again x equal to 9 feet. Why? You have the same point because the second segment starts from there, exactly from 9 feet. So let's plug it and we'll see the values are going to change. Why? Because we have by, now it is pushing. That's why your v is changing at the same point, but m remains same, negative 283.5 feet. Keep it. Then we have x equal to your 21.43 feet. V becomes 0 and m becomes maximum, m max, let's call m max 257.14 feet. And then finally x equal to 30 feet. What we are going to see? V equal to negative 60 cubes and m will be 0 again, external roller. So we got all values. So once you get our all values, next step will be the diagram. So let's go through the equation one more time. So equation 1 and 2, first see. Equation 1 is linear, 2 moment equation is quadratic, so it will be curved. First one will be linear. Then equation 3, it is still straight line, so linear, and then we have quadratic equation, obviously it will be curved. So moment equation all the way will be curved, but shear will be straight line. So let's draw the diagram. You know our important points. V is in cubes, 0 feet, 9 feet, 21.43 feet, very important point, 0 shear point, and 30 feet. So we starts with 0, then negative 63, then moves up to the same point, 87, all straight line. Then again 21.43 feet, it becomes 0, and then it becomes negative 60. So negative 63, positive 87, 0, and then negative 60. X is in feet. A, B, C. Let's do bending moment diagram. Same points are important. M in K feet, 0 feet, 9 feet, 21.43 feet, and then 30 feet. X in feet. A, B, C. So it starts with 0, end with 0, and then it becomes negative 283.5, and it is quadratic, so curved, concave down. Then it becomes maximum 280, 257.14 at 21.43 feet, and then it becomes 0. M max is 2257.14 feet, and this one becomes negative 283.5 feet. So that completes your bending moment diagram. Now I'm going to stop sharing, and then we'll go to your practice quiz. So we see that shear and bending moment diagram, how it can be drawn by using internal shear and moment equation. So let's share again your PowerPoint slide to show you the last slide, which is basically your practice quiz problem. Here is the practice quiz problem. We have shear force bending moment diagram for this again overhanging beam. Now we have triangular loading and then rectangular loading. One segment AB triangular loading, the other segment BC is rectangular loading. I hope this video is useful and you can easily apply shear force bending moment diagram by using internal shear and moment equation.